Welcome, everyone, and thank you for joining us here today. I'm Bettina Heim. I'm a quantum physicist turned software engineer. I'm responsible for the development of the Q# programming language, and I'm leading an awesome team that is building the compiler and runtime infrastructure for it. I'm here with my colleague Sriram, and I'll let him introduce himself.
Hello, I'm Sriram Krishnamurthy at Pacific Northwest National Lab. I'm a computer scientist and a laboratory fellow at the lab. I work on various aspects of compilers and runtimes for high-performance computing. And when thinking about where the next level of performance is going to show up for Department of Energy applications, the natural place was in quantum computing. And that's how I ended up starting to look at quantum computing and how do you efficiently compile and execute quantum programs.
So we are very excited to walk with you through a couple of ideas today. And clearly, when we think about quantum computing, we're not short on ideas about all the possibilities that it can offer. From material discovery to traffic optimization, quantum computing promises a fundamentally different set of tools with which we can potentially solve problems in these domains. But as promising as quantum computing is, we still have a bit of work ahead of us before we can leverage it for applications at industry scale. So if you look at pictures like these, they look awfully similar to the pictures from the early days of computing, like these. Here we see the first programmable electronic general-purpose digital computer, ENIAC, and it could perform about 5,000 operations per second. Interestingly enough, at that time, people were pessimistic about its ability to scale. Today's supercomputer, on the other hand, can perform a couple of hundred petaflops per second. So clearly, computing has truly come a long way. But the question for us is, how did we get from this to this? More than just advances in transistor fabrication, there's a lot that made classical computing as we know it today possible. The question for us is hence, what will be required to bring quantum computing into the era of modern computing, so to speak? Well, in order to enter the era of modern quantum computing, we need more than quantum hardware. We also need to leverage the power that classical computing has to offer, and we need to leverage all the ingenuity that people can offer. We need to leverage each of these assets to its strengths, because ultimately we all bring our unique set of skills, insights, ideas, perspectives, and the vision into this domain. And we need to leverage all these unique assets that each one of us can offer to solve the world's greatest challenges. If we look at computers today, they in many cases can do far more than a single human can do. And part of the reason for that are modern programming languages. Programming languages, in a sense, are the bridges that allow us to share and leverage our collective knowledge. And this is exactly what we set out to achieve with Q#. With Q#, we strive to connect people. We strive to build an open ecosystem with an arsenal of tools to enable this human factor, this human contribution to quantum computing. And for that, we, on one hand, have an open source compiler, an open source runtime, even the language design repository we recently made public. We also provide a lot of different libraries in chemistry, in arithmetic, in machine learning, but resources to get started as well, like samples and katas. We also have dev tools for Visual Studio and Visual Studio Code, interoperability, for example, with Python and other .NET languages, and also an integration into Jupyter Notebooks. But in addition to leveraging the human aspect for quantum computing, we also need to think about where we can and should leverage the tools and insights that we have from classical computing. We need to think about the bigger picture here, about how everything fits together. Quantum computing offers exciting promises regarding how it can benefit society. However, if we think about quantum today, in many ways today's environment is similar to the state of classical computing in the early 1950s. Each system is different and capabilities and resources are highly limited. We face several major technical challenges throughout the stack that yet need to be overcome in order to fulfill that promise. It is not yet obvious which hardware technologies are likely to succeed or which applications will ultimately benefit society. So to advance the field of quantum computing, we need to think beyond just how to build a particular end-to-end system. Instead, we need to think about how to make it possible to easily connect emerging technologies. We need to think about how to grow a global ecosystem that facilitates to develop and experiment with different approaches. So how do we connect vastly different emerging technologies? Let's look at roughly how a quantum program gets translated into instructions for the quantum device. Obviously, we start with a piece of code that is then translated by the compiler into an intermediate format, based on which an executable is built for a specific target. During execution, the instruction sequence for the quantum processor is generated and executed. And I'll omit the lower levels of the stack for the purpose of this conversation. A good point to define a common interface is here. Why is this a good point in the stack to choose to connect different front and backends? Well, for one, at this stage, we are both front and backend agnostic. All the language-specific pieces already are compiled away, and what remains is a way to represent the information that is relevant for execution. On the other hand, a lot of the target-specific information is not yet incorporated beyond the very basic information, like, for example, the quantum instruction set. But furthermore, more involved applications may actually require that there's a repeated communication between the runtime and the quantum processor. So if we want to enable that and facilitate that, then it's important that these pieces stay connected. So defining the interface one level above that actually enables to do just that. A common interface between different front and backends hence needs to be able to represent all classical computations in addition to the quantum pieces of the computation. And indeed, we just recently made a first draft public with a specification for a quantum intermediate representation that serves precisely this purpose. In particular, with the quantum intermediate representation, we can represent things like repeat until success-based algorithms, like this one here. And even more, we can make it possible to actually execute that on today's quantum hardware. The reason that this is interesting is that in this case, for example, we indeed do computations based on measurement outcomes while the quantum state remains coherent. And that enables a lot of exciting work. So what is this QIR, short for quantum intermediate representation? QIR is a language and hardware agnostic format within the LLVM, meaning it defines how quantum programs are represented within LLVM. This, of course, prompts the question, well, what's LLVM? It is a mature open source compiler framework that is widely used in classical computing. You might wonder why we chose to represent within the LLVM IR rather than a custom format. For one, at the IR level, what we need for quantum is not that different than the tools that are needed for classical compilation. Leveraging the existing LLVM toolchain grants us access to an arsenal of mature tools, for example, for dependency management and tracking. These tools we would otherwise need to recreate from scratch. So to summarize, QIR defines how to represent quantum programs within LLVM. It does not require an extension or a modification, and all the tools that already exist and can be leveraged are available for use. More importantly, QIR is not specific to Q#. In fact, any programming language for gate-based quantum computing can be compiled into QIR. Similarly, QIR is hardware agnostic. It does not make any assumptions or require a particular quantum instruction set or gate set to be supported, but instead leaves it up to the target environment to define that. QIR thus defines a foundation for developing optimization passes and code transformations that can be shared across different languages and backends, and facilitates integration between different frameworks. In terms of quantum execution, QIR allows for arbitrary interactions between classical and quantum computations. It therefore makes it possible to really represent the full range of quantum applications, from things that run on today's hardware, which can be translated into a particular profile or subset of the QIR, to large-scale applications for future devices. So we follow with that in the same ideas that already exist in classical computing, where we've got the front end, different languages, compiling into a common IR format that is then supported by various backends. And indeed, many classical languages have an LLVM-based compiler. So building on top of that toolchain, for one, permits us to integrate with and use libraries or backends written in these languages. And I'm very happy to hand off to Sriram here, that will tell us in more detail how that looks like and what exciting possibilities that unlocks.
Thank you, Bettina. Now I'll talk about one instance of our joint effort that benefited from this quantum intermediate representation. So this is a piece of work that we've been doing for several years, focused on this notion of how do you program large-scale parallel systems. And commonly what we do is we think about CPU as the unit of execution, and we program a parallel computer consisting of a collection of CPUs. But then going forward, we expect that computers are going to be built with a combination of CPUs, GPUs, custom application-specific logics, and all of these in a heterogeneous fashion. But one of these has already become very popular, which is that we are already building systems where the GPUs form the bulk of the performance available on many of these machines. So we want to think about programming these in a GPU-centric fashion, where we first think about how do you maximally utilize the GPUs you have on a given machine. To give you an example, the largest open science machine we have in the Department of Energy complex, the OLCF Summit, is powered by GPUs. But then going forward, the largest supercomputers we have in the United States are all going to be powered by some form of GPUs. Now, while the technologies available in each of these platforms might change, in all of them, the goal to get the best performance out of these is going to be to use the GPUs in as efficient a way as possible. And key to that is to have this long-running, non-interrupted execution of the computation on the GPU, rather than thinking about the CPU as the primary and then repeatedly offloading computation from the CPU to the GPU, transferring the data back, and so on. To achieve this, we have been working on adapting the bulk synchronous processing, or BSP paradigm, for these multi-GPU clusters. To give you an idea of what this BSP model is, it's a very simple computation model that consists of two phases. First, there is a compute phase where you have a processor, here shown as P. Each of these processors is going to operate on data available in its own local memory, shown here as M, and that's one phase. And once all of the processes have finished their computation, then they use the communication network to exchange messages to all the other compute entities that we have. And once the communication is done, they reach a barrier and then start over again. So they go through a compute phase and a communication phase in this alternating fashion. It's a very simple but powerful compute model that we've been using as the foundation for parallel processing for decades now. We focused on the development of a multi-GPU BSP model with 4 objectives. We wanted the infrastructure and framework that we developed to be of high performance so that we are maximally utilizing the GPUs. We wanted to scale where when we add more GPUs, we are naturally going to exploit the parallelism available so that we are going to effectively utilize larger and larger systems, be it one node with the few GPUs we have or 10,000 nodes in a large-scale supercomputer. We wanted to be easy to program, and our goal specifically was to have the difficulty or the challenge of programming, let's say, a 10,000 node GPU cluster to be no different from programming just one GPU. And finally, we wanted the infrastructure that we develop to be portable across a large class of GPUs, interconnects, and system architectures that we can develop. We demonstrated this idea in the context of deep neural networks in a paper that was published in SE 2019. But then we turned our focus to quantum circuits and quantum programs. So we wanted to see how we could use this idea of multi-GPU BSP programming to efficiently execute quantum programs on these large-scale GPU platforms. To do that, we developed what we call DMSIM, a density matrix quantum circuit simulator. So the input to the simulator is a quantum program which defines a circuit. And then given such a program, we take care of all the details of efficiently executing it on the target platform. And it's not just one target platform. We look at the specifics of each of the platforms, be it a couple of GPUs attached to one CPU, a few GPUs in a specific topology, attached to a switch, or a large-scale compute cluster that consists of multi-node GPU socket components. And we put in a significant amount of effort to make sure that the implementation we have achieves the best performance. And here, for example, I'm showing the roofline plot where we show that our execution is essentially bound by the peak bandwidth that's available on, for example, this particular GPU platform. Now, we have a good infrastructure, but then how do we make it usable for an end user? And this is where the quantum intermediate representation that Bettina talks about comes in. So we could write a program in Q#, and through the intermediate representation and the QIR bridge that was developed by Bettina's team, we could then naturally execute any Q# program using the DMSIM simulator such that it's efficiently executing on a variety of target platforms. So on the left, for example, is a Q# program that you could write today, and then you can compile it down and then run it using the C++ based backend that we have for the density matrix simulator. To summarize, we went from a Q# program to a variety of target platforms. Here I'm showing here multiple GPU architectures using the quantum intermediate representation. And you can reason about these Q# programs using the best performing tools on the systems you have at hand. But to step back, I think there is a bigger implication of all of this work. It is that the quantum intermediate representation lets us decouple the communities that are building programming languages, applications, and algorithms for future quantum computing problems from the communities that are looking at the specifics of a compilation strategy, specifics of architecture, simulation, or techniques for reasoning about these quantum programs. Using the quantum intermediate representation, we believe these two communities can advance concurrently while immediately leveraging the advances that the other community did rather than waiting to figure out how do we put these together. For example, in our context, we can continue to work on newer architectures, newer techniques for simulation, and even newer classes of simulations without having to worry about the input format, how do we hook up with different programs, is our input language matching the needs of the specific application we are talking about, and all of that. Bettina and her team can take care of all of those details while we focus on work, and we know that because of the QIR intermediate representation, we can just take any Q-sharp program and then demonstrate and evaluate what we are doing using our simulation platform. With that, I'll turn it over back to Bettina.
Thank you very much, Sriram. And clearly, we're of course very excited about this work and having been able to facilitate this collaboration. One might still wonder, well, why is QIR important? Or what is it useful for? Well, QIR is important because quantum computing is still in its infancy. Sriram has very nicely outlined how we can really benefit from all the possibilities that we have in the computing space in general. But the quantum computing community itself is still tiny compared to the broad computing and programming community. More importantly, computing has grown in ways that would have been impossible to predict back in the early days. So if we want to emulate and accelerate the similar progression for quantum computing over the next couple of decades, not only do we need to take full advantage of the classical tools and resources at our disposal, but we also need to leverage the insights into how computing itself has evolved over the course of more than half a century. We have the tremendous advantage today of having the hindsight into what the essential success factors were that made that growth possible. So in the coming years, we expect there to be exciting advances in how classical and quantum computations can interact at the hardware level. With QIR, we provide a foundation for developing software frameworks that can target today's devices and more powerful systems in the future. Beyond that, we provide an infrastructure to allow integrating exciting projects such as the one presented here in a way that will unlock advances in quantum algorithms and applications. With that, we would like to thank you very much, and we will both projects will be very happy to get contributions, feedback, questions, anything. All of that is on GitHub, open source. On one hand, the DM-Sim that Sriram has presented, and that project can be found at the given link. And on the other hand, also QIR and Q# itself are both on GitHub. Thank you very much for your attention, and we're looking forward to a lot of exciting projects.